What Muon g-2 is trying to understand is if we understand particle physics.
Are there new particles, new forces we haven't yet discovered in the universe?
It's looking for interactions of the muon with some unknown particle that would be new physics that goes beyond the standard model that we know and love.
The muon was sort of the first particle we discovered that really broke the mold. Because the muons are 200 times heavier, you're 40,000 times more likely to make this quantum foam when you use a muon than an electron.
So it's kind of in a sweet spot. We can make tons of muons, and we can do ultra-precise measurements of muons, more than you'd really be able to do with much heavier particles. When we make a measurement and compare it to the prediction, it's kind of like a go, no go for all the knowledge we have. It's, do we understand particle physics, yes or no?
So with Muon g-2, what we're actually doing is measuring the magnetic moment of the muon, because this sea of particles that's constantly fluctuating in and out of existence effectively changes the magnetic moment of the underlying muon. You can think of the magnetic moment as being sort of the dipole moment. If you ever had a bar magnet with a north and a south pole, every individual muon is like that, with a sort of its own internal bar magnet.
We're looking at what happens to this little bar magnet when we put it in a magnetic field.
The first measurement of the magnetic moment of the muon took place way back in the 1950s. Leon Lederman, who was a former director of Fermilab, was part of that experiment. That continued through a series of experiments at CERN in the 1970s, culminating in 1979 with the CERN-3 experiment, where they pushed the precision, their ability to measure this quantity, this magnetic moment of the muon, to a precision of 7 parts per million. After the experiment ended at CERN in the 1970s, the next generation took place at Brookhaven National Lab. And the goal there was to push the precision even further, so it was 14 times better than the CERN experiment. And furthermore, it left the field with a bit of a mystery. It was enough to make everybody in the field wonder, are we creeping up on the discovery of a new set of particles through this precision measurement of the muon's magnetic moment?
The experiment was moved from Brookhaven to Fermilab. The cryostat is big. On a highway, it would take 4 lanes of highway, and we're not allowed to take it apart. We're supposed to leave it as intact as possible.
It entailed shutting down 2 different interstates and the Chicago area on 2 different nights.
People came out to watch, and we were overjoyed by all of the interest in it. It was so special because the people working on it, all the planning that went into it, and all of the attention we got from it, that was totally a surprise to me.
We were a young team. We used to joke that we needed a grown-up on the team because none of us had ever done project management before, and we were kind of making it up as we went along. It was perfect to bring it here and reuse it. It would have been significantly more expensive and difficult to try to recreate a similar device here. The Fermilab campus had previously been focused on the Tevatron collider, where we collided protons and antiprotons. And so for the g-2 experiment, we took what used to be the antiproton source and converted it to a muon source.
It was a challenge to see if we can do better. Once we put the beam into the ring, we figured out how to stabilize the beam a lot better.
The powerful accelerator complex at Fermilab was capable of making 20 times the muons compared to what was done at Brookhaven.
It felt like a fire hose. We would just start filling up with muons like gangbusters.
At the same time, I think we did recognize that this was a very important experiment that could potentially find physics beyond the standard model.
So when you get to the final result, to us as experimentalists, a really important part of that is we met our initial goals that we started writing down in 2007 when we were almost making best guesses of how good do we think we can really do on this experiment.
And for me, it's still the only project that I've been involved with sort of from beginning to end. It's really been maybe the best experience of my career.
Being part of Muon g-2 almost undoubtedly be the highlight of my career.
It's been an honor, definitely a highlight of my career.
Muon g-2 is a huge part of who I am today, and it's just extremely gratifying to know that the Breakthrough Prize Committee selected this beautiful little experiment for the award this year.
What I remember most are the people and the friendships I made. It's been a pleasure and a privilege to be a part of it. I'm just so happy for everybody on the collaboration, the grad students and the postdocs and the engineers and technicians.
I think this award is really nice recognition of all the work over the years that has gone into this measurement, and I'm proud to be a piece of that.
I would say by far one of our most important byproducts is our ability to inspire future scientists. It all sounds like science fiction until you realize it's reality.
You know, there's different levels of recognition for accomplishments in the field. There's peer recognition, which is actually to us the most important. And then there's being recognized, outside of your immediate peers. And it's a very nice feeling. We're all very touched by the award.